Chapter 10, Wireless Communications, Part 2, Frequency Modulation. In frequency modulation, we modulate the frequency of the carrier signal, not the amplitude. And it is modulated by the instantaneous value of the voltage multiplied by a constant. So as we go along the wave, as the voltage is going up, it is increasing the frequency. So at this point at the top here, that will have the highest voltage, so that will have the highest increase on the frequency, which will be somewhere around here. These graphs don't match up perfectly. And then as we go down, the frequency will be decreasing until this point here. That's where it will be negative, so the frequency will actually be decreasing, and that will be somewhere in this bit here, using the physics term rarefaction, where it's the most spread out. And again, as we go up, about this point here, it'll be the most compressed, so that'll be around here. Notice that the amplitude is not at all modulated. This is really, really important. If you are given the first two graphs in the exam and asked to sketch the third, then you need to draw these dotted lines with a ruler and then draw the carrier wave in. They will penalize you if it's not clear that the amplitude has been kept flat. We talk about the maximum change from the carrier frequency, and this is called the frequency deviation. So this is the highest point here. Remember this value, this voltage is being multiplied by a constant, but the frequency deviation is the amplitude of the information signal, so that maximum voltage multiplied by a constant. We'll come on to that in a second. So that's the definition. It's really important because we'll keep using that idea. The constant you will always be given, so we are given it in this question. The frequency deviation per volt is 25 kilohertz per volt. I would recommend that you pause the video at this moment in time and you have a go at this question. Okay, let's have a look through this question. So the first thing we want to calculate is the frequency deviation, not the frequency deviation per volt, but the overall frequency deviation. So that will be 5 volts, the amplitude, multiplied by the 25 kilohertz per volt. The volts cancel in terms of units, so the frequency deviation, so this is the most the frequency is being altered by, is 5 lots of 25. Sorry, I've misread the question slightly. It's 3 lots of 25 because 3 volts is the information signal. So it's really, really important that you are reading through your questions carefully. So it is the information signal that is doing the modulation. So that is 75 kilohertz. Now the carrier frequency is 400 kilohertz. So we have at a minimum value, so the minimum frequency when it's the most spread out will be 400 minus the 75, which will be 325 kilohertz. And the maximum frequency will be adding this value, so we 400 plus 75. So the maximum frequency will be 475 kilohertz, and that's where it's the most compressed. And it's the 3 kilohertz is to do with the frequency of the information signal. And we could work out the time period, the sort of time it takes for it to vary from 325 kilohertz or to 475 kilohertz back again, and that would be 1 over 3,000. So if you wanted to work out how quickly it would be changing, it would be in a 3 kilohertz speed. That's how quickly it would be becoming compressed and stretched out, compressed and stretched out. That's just the just an important point to note. So that's that value, that 3,000 times per second, that's 3 kilohertz. The voltage of the carrier signal, which is the modulated wave afterwards, at 5 volts is unaltered. That doesn't change. Okay, we will want to measure how much modulation we've got. And there are two kind of factors that have a big effect on this. There is the frequency of the information and the frequency deviation. The frequency deviation tells us how far we have deviated from the carrier frequency. So the higher this is, the more modulation we've got. The information frequency tells us the maximum frequency present, so that tells us how quickly we're making this change. So if this is very large, then the modulation is quite small, because we are going compressed and then spread out, compressed and spread out really, really quickly. So the modulation is to be quite small. So that brings us to the modulation index beta, which is given on your data sheet. Do make sure you now label this on your data sheet. And the higher the beta is, the more modulation we've got. So this is beta equals 3, which you can kind of see it's compressed there, it's spread out there, but it's almost tricky to see. It's not very well modulated, well, not very high modulated. Beta equals 5, you can see is much more modulated, much bigger spread, and much more compressed. And beta equals 7, even more so. And we don't need to know the FM graphs for level electronics. They are very complicated with lots of sidebands. The graphs on the right, sorry for the typo there, give an idea of the number of sidebands present. So the bigger beta, the more the modulation, the more sidebands you've got, and you don't need to know how many there are. The sidebands are one lot of the information frequency away, so that's the carrier frequency -1 plus 1, that's -1 plus 1, that's -2 plus 2, and if you increase it up further, you'll end up with more. Now, an interesting thing to note is the fact that carrier frequency isn't always the biggest frequency. And this is an important idea. I'm going to come back to that slide in a second. The reason why this is important is that means that the power of our signal, much more of it is going into the side bands. And that means that it is a more effective and efficient way of sending signals than AM, where most of the power is actually just going in the carrier, which at the end of the day is just a sine wave. It's not something we actually want to hear. It's also important to note that this is a constant power wave because there is a constant amplitude. So we're not altering the amplitude of the voltage, so it is a constant power wave. Okay, so bandwidth. Then you are not expected to know the maths behind this. By all means, go and have a look at it. It's quite interesting. But the number of significant sidebands is given by 2 lots of beta plus 1. So the bigger the modulation index, the more sidebands we've got. And the factor of 2 is because we've got a doubling effect. So we've got half on one side, half on the other. So that's why we've got a factor of 2. And to work out the bandwidth, we then need to multiply this by the maximum frequency of the information signal. Now remember that beta is equal to the modulation index is equal to the frequency deviation divided by the maximum frequency of the information. So you can replace that in there and then multiply through, and you will end up with the second equation. Please do make sure you label this on your data sheet. Okay, that is it, really. That really is all you need to know about FM modulation. So let's have a look at some example questions. I would recommend that you pause the video in each case, you have a go at this yourself in your notes, and see how you get on with it. There are 5 questions. Please do make sure you write them down, particularly the last couple, as they are particularly tricky and interesting. So reading through this question, there's a lot of wordage. We're told, for instance, that wideband radio has a large bandwidth, but that doesn't really tell us anything. We are told that the frequency deviation is 75 kilohertz. And we're also told that the information baseband goes from 20 hertz to 15 kilohertz. Now remember, we always really just look at the top one. 15,000 minus 20 is 14,980, which is basically 15,000. It's 15,000 to 366. So we always just look at the biggest value. So picking out the key information from the question, we've got that this is 75 kilohertz, and we've got that this is 15 kilohertz. And we're asked to find the modulation index and the bandwidth of the signal. So we plug these into the equation. Remember this equation, or at least hopefully you got it written down and you got it on your datasheet in front of you. So that would be 75 over 15. They're both in kilohertz, so that will cancel. So 75 over 15, putting that into a calculator is 5. So modulation index of 5. And bandwidth, again, it's just about putting it into the equation. Bandwidth, of course, does have the same units as the figures you're putting in. So that's the first question. We've got questions 2 and 3. Again, I'd recommend you pause it before we move on, before I go through it. Okay, let's have a look at question 2. A lot of information here. There's 3 numbers. So we've got the carrier frequency. So that's FC, not the frequency deviation, it's just FC. This is the information signal. And this is the frequency deviation. Calculate the bandwidth. So we know this equation, we put our values in. We then plug it in a calculator. Make sure that your units are the same. That is important to note. And we get 80 kilohertz. Okay, question 3. An audio signal has a baseband from 200 to 4 kilohertz. Again, we ignore the bottom end. We just look at the top. It's really not worth bothering with the bottom end. It modulates. So this is Fi. It modulates carrier frequency 50 megahertz. So that's Fc. The frequency deviation per volt is 10 kilohertz per volt. And the maximum audio voltage that can be transmitted is 3 volts. So this is the frequency deviation per volt. So divide by the voltage, and this is the voltage. This is the maximum voltage. So the first thing we're going to need to work out is the frequency deviation. We're nearly always going to need that. So that's going to be this 10 kilohertz per volt multiplied by 3 volts. So that's 30 kilohertz. And then asks us to work out the bandwidth. So we put it into this equation, which you've already seen a few times by now. The important thing here is to make sure you don't get in a muddle and that you pick the right values. Okay, question 4. You may well be asked to analyze a graph and work out the information frequency and the carrier frequency. So again, I would recommend that you pause this video and you have a go at this question.